Want to see something? Want to see something? So we're at the very beginning of kinetics. So let's start off with a little reaction here. I've got a couple different chemicals that I'm gonna dump. They're both clear. So as I dump the clear into the clear, they're still clear. So what's interesting about the start of this is that it's a no reaction. All right, if you I don't know if this you can state it if you need to. It's a no reaction, but what's interesting about that no reaction situation is that the beaker is now full of spectator ions. Nothing happened. There's just a bunch of charges floating around. So what if we added two more chemicals together? Let's see what happens now. Now, I know what you're thinking. Hey, cool, Cummings, you made vomit. But as I start to introduce kinetics for you right now, keep staring at that. But listen to my words as you watch. As the first slide says, kinetics is a look at the rate at which reactions happen. You are really used to fast reactions. We're always time pressed in here. So usually you mix stuff together and a reaction takes place. But there are some reactions that take a very long time to go. This one's not very long, but it's certainly delayed. Because as you continue to stare at it, you're going to see that while you can still get hints of vomit, that green is about to become more of a Gatorade type green. But not only will it become less of an offensive green, it's going to clear up in a moment. You're going to be able to see straight through that solution. But then the kinetics are going to allow the green to go blue. And if you keep watching, you're going to get purple and red. So be patient with it. The reason this works like that is I dumped all those ions that weren't doing anything, bunch of spectators. And then we had reactions happen that created new products that reacted with some of the spectators. Then that reaction created new products that reacted with other spectators. And I was able to dictate the kinetics of this reaction to go through a bunch of different reactions, one after the other. Our focus in this unit is not only to say, okay, cool, well, there's ways to control different speeds of reactions, but all of the different angles that you could look at when considering reaction speed. So let's start really simple with just what different ways we can express some speed of reaction data. Now, I want you to look at these two items over here. And what you'll notice is that one says product, one says reactant. Because it turns out that when you're focusing on the speed of a reaction, you can pick whichever side you want to. The reactants are going to be used up, while the products are going to be, well, created, right? So whichever side you focus on is up to you. They'll give you the same kinetic data. But I do want to make an important distinction that while some reactions are fast and some are slow, rates are always positive. You can't have a negative rate. To have a negative rate would be to go back in time. So while something might go really, really fast, it's never negative, which is why if you look at the difference between these two expressions, one looking at products and one looking at reactants, do you see the negative symbol on the bottom one? If you missed that, make sure that negative symbol right there is in your notes. Because here's what it does mathematically. We know that the change in products is always going to be positive because you create products. The change in reactants, well, they're consumed, but we can't have a negative rate. So what can you put in front of a negative to make sure it stays positive? Another negative, which is why that saves the algebra. I also want to point out that change, delta always means change in case you don't know that. But to find the change in something, it's always final minus initial. What do I mean by that? Well, let's say that we wanted to like find distance traveled. And let's say that I started on mile marker 2 and I walked down a road to mile marker 7. What would you do specifically to figure out the distance I traveled? 7 minus 2, right? My ending spot minus my starting spot. Because that's how you find the change in anything. So delta always assumes final minus initial. And then finally, in case you missed it last year, brackets mean molarity. If you ever run into an expression that looks like this, that is automatically 0.88 molar. So the brackets that are in those expressions always mean molarity. You don't even have to put units after it, and it's still right, because we know that brackets are molarity. Now, that reaction that I showed you, if you want to see another cool thing that it can do, if I can get this angle right, as I stop the kinetic movement here, it's going to cycle back through the colors in reverse. Just got to tap it. There it goes. Yeah. But then if you put it back on, it'll go right back through and we can get all those reds and purples to come. Oh, hi. All those reds and purples to come back. Yeah, it's being class. Sorry, I guess. But anyway, let's keep going. Now, if we start to apply kinetics to an actual equation, what you'll find is that you already have the ability to tell me some kinetic data. If you look at this equation, the coefficients tell you the kinetic conversations that the substances are having. This has 2 dinitrogen pentaoxides producing 4 nitrogen dioxides and oxygen. But if you look at the coefficients, what you'll see is that the first product, the nitrogen dioxide, is being created twice as fast as the reactant is reacting. Do you see that ratio? 2 to 4, twice as fast. There is kinetics there. What's true about the other product then? Half as fast. Yeah, it's a 2 to 1. So this oxygen is being created half as fast as the reactant is decomposing. So we've always been able to assign kinetic information to coefficients. I'm done being amazing. In that way. But while that's great and all, I want to show you more of a question-based way that College Board can see if you understand the mole ratio connection to kinetics. If you look at this new slide, you'll see at the top that we've got A reacting with B to form C and D. But not only that, it gives us the coefficient of the first reactant. The other mole ratio parts are variables that it wants us to find. But then it gives us rates, which is something that you have not seen before. All right? It gives us a rate of the first reactant of negative, because it's a reactant, right? So it's got to be, it has to be a negative change, not a negative rate, of 0.05 moles per liters. What does that S stand for? Seconds, because now it's time, right? Now time is a big deal for us. So moles per liters is molarity, and it's the change in molarity over seconds, since now we're looking at those kinetics. But we've got values for everything, all right? So we've got all of these other values with the same units, mind you. And what we can do is apply these different rates, or rather compare them to each other, to easily find the other mole ratios, or the other coefficients. Let's compare these two together. Remember, it's always a comparison, right? Just like on the previous slide. Now, some of you are going to be much better at this just seeing it than others. There is never shame in using a calculator. But here's a trick. If we slide the decimal to the right twice, these become 5 and 15. How much larger is this number than that number? 3 times. It's 3 times larger. 5 goes into 15 3 times. That means that the rate of B is 3 times faster than A. What must that coefficient be then? It must be a 6. If the rate of A is 2, 3 times that is 6. Now, I don't want you to think, oh, so you just compare everything to A? You can, but you don't have to. Everything talks to everything. So to find this coefficient, let's do B and C just to prove it. Look at these two numbers. Now again, calculator's your friend, or if you slide the decimal twice, it becomes 15 and 7.5. How would you describe those numbers? 7.5 is what of 15? It's half of it. 7.5 is half of 15. That means the kinetics here are half of the kinetics there, which means the coefficient must be 3. Yeah, if this coefficient is 6, half of it would be 3. Somebody yell out D. D. Nice. Jokes and teenagers. What's the answer for D? Oh, come on, somebody yell it out. You can use any of them. It's 1. The coefficient is 1, which I'm not going to show that, obviously. But look, this is a third of that. All right, so 1/3 of 3 is 1. If you compare D to B, it's a 1/6 of that rate. And it's half of that rate. All of them giving 1 as the coefficient. Do you see how I'm doing this? Now, the backbone of kinetics is rate laws. Rate laws are awesome things that tell us very, very useful data about the speed of any reaction. But in order for you to appreciate it, you need to understand the anatomy of what goes into an expression. So that slide has it's got a fake rate law, but let's use it and just identify what is what. All right, so the fake one is going to be rate The whole point of a rate law is to do some math to tell you how fast the reaction is going to go. So it's rate equals, and then there's all the things that we have to multiply together. The first thing is K. I'm going to come back to that because that takes an extra second to understand what K is. Let's talk about the other two things. There's brackets, which mean molarity, right? Those are reactants. In this case, it's NO and O2. But whatever items are inside the brackets there are the, oh, I'm sorry. My bad. Whatever items are in those molarity brackets are the reactants of the reaction that you're looking for the rate of. All right, so always reactants. Now, there are little exponents that go up there. We called that the order. I'm going to show you in about 15 minutes how we calculate those. But just for introduction's sake, I'm going to make a couple up. I'm going to make up a 2 and a 3. And I want to explain how that 2 and 3 are useful. Here's what order tells us. The comparative orders of the reactants tell you the importance, the power of those reactants to the kinetics. Like, for example, let's say that whatever this reaction is, I'm still making stuff up, that whatever this reaction is the ingredients, the reaction to make root beer. All right, you're just listening for a moment. Don't write that. Let's say that this was the rate law for making root beer. And I got all the stuff. I'm like, hey, we're going to do this today. And I got the stuff out in the back. And while we were back there, somebody burst into the door and yells, Cummings, the world just ran out of root beer. We need you to save everything and make a bunch of root beer. And I'd be like, oh my God, I've got all the stuff out. Like, this is perfect. I'm ready to make root beer. But they're like, no, you don't understand. Like, people are dying. We need it right this second. What I would do is I would look at the rate law of the root beer and I would identify which reactant is more important in the kinetics, which one's controlling the speed more, and it's whichever one has the higher order. So if I can only dump in one of the reactants, more of it in that moment, it would be the chlorine. Because in this made-up example, the chlorine has the higher order, therefore that reactant has greater power in controlling the speed. The other thing you can do at the very bottom is while the reactants have their own orders, that again, I'll show you where the real numbers come from. The reaction has an order also. In order, we all quit with the paper. Sorry, y'all are annoying me. The order of the reaction is found by adding up the order of the reactant. So, what would, that's real simple. What would the order be here of the overall reaction? Yeah, this would be fifth. 2 plus 3. We won't be dealing with any fifth orders, but just for argument's sake. Now, I skipped K. Look here. This is not important today because mechanisms, what we're about to learn, you can't get K with them. But I want you to understand why rate laws are awesome. These are molarity brackets, right? Here's what we could do with this. If we were going to mix nitrogen monoxide and chlorine together, I could just pick some molarities. I could say, you know what? I'm going to do 0.5 molar and 2 molar. If I popped those numbers in there, raised them to the powers of their real orders, and then multiplied it by whatever K is, which is a constant value, it's published in a book already. You could go and look up the rate constant for NO reacting with Cl2, and it will give you a value to use for K. And if you grab that number that scientists have already found for us, and you plug it in there and multiply those other numbers times each other, it'll tell you the speed of that reaction, which is super useful and awesome because we've got a K value for pretty much every reaction there is. It's the number that when mixed with your molarities and stuff through multiplication it all marries together to actually give you a real life rate. More on K later, but he's always in that spot. All right, so what we're going to be focused on for a big chunk of this unit is, well, how do you write a rate law? Like, how could you look at a reaction and be like, oh, well, the rate law is written like this? And there's different ways to do that. Our focus today is what's called a mechanism. By definition, a mechanism is all the chemistry in a reaction that you never cared about was happening. You know what you're used to? You're used to reactants yielding products. But that's not what happens. Really, this moves over here, then this marries with this, then this detaches and goes and loves on him. There's all these little baby steps that happen during a reaction that we've never focused on, called the mechanism, and today's the day. Here's an example of a mechanism. It's these 3 steps here. Up here, they've given me the reaction. So there's the reaction, and then there's those little baby mechanism steps that you're now seeing for the first. I need to show you a bunch of ways, a bunch of information we can get from these mechanisms. So if you're feeling a little sleepy on a Monday, stand up and stretch or something, or you can go sit in the back of the room even, but I need you to refocus your energy because this is important. A lot of times what College Board likes to do is they like to not give you the overall reaction. What they like to do is give you the mechanism and have you derive it, the reaction. Here's good news for you. In this class, you'll never be asked to write a mechanism on your own. You need way deeper chemistry knowledge to do that. So I'll never give you this and say, write that. No. That's not your job. The mechanisms are always given, but I will ask you to take a mechanism and figure out what reaction it's representing. So here's the steps to do this first part of an analysis. It feels a little spectator ion-ish because what we're going to do is we're going to compare the different steps of the mechanism, and any time that you find a reactant anywhere that is a perfect match of a product anywhere, we're going to draw a line through it. Now, this might be the most important thing I say all day. We're going to be like crossing stuff out, and in your brain, you're going to be like, oh, we're eliminating it. No, we're not. I can't stress that enough. We're going to start drawing lines through these things. We're just thinking about it. I'm showing you a way to figure out chemistry. This is the mechanism. You don't get to eliminate stuff. It's all there. It's all there. The lines that we're about to draw through is just to figure out this vocab, all right, intermediates and catalysts. Realize that while I might even use the phrase eliminate, you are not eliminating anything. You're just thinking about how stuff interacts using lines. Here we go. Anytime a reactant anywhere matches a product anywhere, I'm going to draw a line through it. Like, look here, look here. See, hoi! See him? You see how there's another hoi right there? They're both identical copies. One's a reactant and one's a product. Does it happen with anything else here? What? No. Hydroxides. Now, this is tricky. Don't write this. You see the two OH minuses. Realize what coefficients are. This is really saying there's an OH minus and an OH minus. There are two OH minuses. That's what it is. Look on the other side. Do you see the two OH minuses? So these two OH minuses take care of that. They're perfect copies. Now, if there was only one OH minus over there, you could still cross it out, and then you would cross out one of those, right? It's kind of half reaction-y in regards to the way that we were combining there. Someone said iodine with I minus, and that is wrong. So focus here because y'all make this mistake a lot. they have to be perfect copies. Iodide and iodine are very different things. You see how the hydroxides both were -1? So they were perfect copies. You see how the HOI were both neutral? Perfect copies. I- and I2, imperfect. They are not the same thing. There is no elimination. Nothing else can be eliminated based on these rules. But what I can do now is I can figure out the overall reaction that, again, I gave you, but they usually don't. Look. See the H2O2? There he is. You see the 2 I minuses? There's 2 I minuses. Check it out. See that at 2 H2, I'm sorry, 2 H pluses? Yep. And then on the product side, iodine and 2 waters. Iodine and 2 waters. We can derive the overall reaction from our analyzed mechanism. Now, I've got some important vocab here. Intermediates and catalysts. I'm going to say this a couple times. For some reason, these items bounce off your brain. So look here. Don't write. Give me, I want your hearts. It sounded very Halloween-y. In order to identify intermediates and catalysts, here's the definition. Listen, an intermediate is something that was made during the reaction, but then used up before the reaction was over. A catalyst is something that was present at a part of the reaction and still present at the very end. You've studied catalysts before, right? You studied enzymes in biology. You know that the definition of a catalyst is something that speeds up a reaction without being used up by the reaction. So by definition, a catalyst should still be there at the very end of the reaction. Those are the definitions. Here's how you find them. Keep listening. To identify them. To identify them. That was really good time. You focus on just the products. Listen, to identify intermediates and catalysts, we're looking at just eliminated. They're not really eliminated, right? We just put a line through it. They're still there. Eliminated products. If you drew a line through a product, not in the last step, like there's step 1, step 2, step 3. If you drew a line through a product, but not in the first step, it's an intermediate. If you drew a line through a product and it was in the last step, it's a catalyst. Let's see if you listened. Looky. Remember, to find intermediates and catalysts, it's products only. So I don't care about that. Hey, look, an eliminated item. As a product, is this the last step? No, it's the first step, which means it's an intermediate. Because if you eliminate a product and it's not the last step, it's an intermediate. Hey, look, an eliminated product. Is this the last step? Nope, it's still step 1, right? There's 3 steps. This one's also an intermediate. I don't care about the reactants. Hey, look, and another eliminated product. Is this the last step? Nope, it's the second step. So what is that? Another intermediate. Because intermediates are any eliminated products that are not the last step. All right. Do you see anything else we can label? No, because we're only looking at the products. This mechanism has 3 intermediates and no catalysts. Again, the intermediate is something that was formed during the reaction and used up before the end. I formed both of those things, but then they were gobbled up by other steps of the mechanism before we got to the end of it. Yes?
Could there be a reaction?
No, there will always be at least one intermediate, but there does not have to be a catalyst. Good question. How are we doing? We all right? It's a lot, because we got more to do. Another thing that we could be asked to do with the mechanism is draw an energy profile. Here's what an energy profile. Now, here's what I'm going to do. I'm just going to draw the energy profile, and then we'll talk about why I did what I did. So, the energy profile is going to plot energy versus time. All right, we're plotting energy versus time. And here's what it would look like for this mechanism. Why do you think my camel has 3 humps? Because there's 3 steps. So here's the first thing. For every mechanism step, your energy profile gets a hump. Why do you think the first hump is so big? Yeah, you see this? You see this right here? This slow step that it says? All right. It's labeled as the slow step. And it turns out it's actually a really big deal. The slow step determines everything. It determines the rate for the entire reaction. Because if this was a track that you were going to like race on, if you were to start here and run the track to the end, and at the end I was like, hey, which part of the race do you think controlled your speed the most? You'd be like, the first part. The first part killed me. I didn't even care about the other stuff. Because the slowest step determines the rate for everything. Because of that, we've got a special name for it. We call this slow step the RDS, which stands for, as you already wrote down, the rate determining step, because that is the slow step. So that's the energy profile. You could splash intermediates and catalysts into that. They don't really ask you to do this often, but what I mean is, first off, keep in mind that intermediates and catalysts can only exist at the end of steps, right? As products. So here, I could say that there is an intermediate and another intermediate right there at the end of the first step. There's another intermediate there at the end of the second step. And you could write what it is too, like hydroxides and the Hoy. And then what was at the end of the third step? Yeah, nothing, so you wouldn't label it, but you could mix that in with your energy profile. But the real end game is the rate law. Our ability to write a rate law is the most common thing that we have to be able to do. So let's actually write one. Now, you might need to look back a few slides because the format's always the same. It's always rate equals K. So right away, it's rate equals K. But then what went next? Brackets with reactants in them. And here's where it's a big deal. Looky, looky. The reactants that go in those brackets are the reactants of the slow step only. So there will be brackets, but in those brackets, I'm going to go to the slow step, which has hydrogen peroxide and iodide. Those are the 2 reactants in the RDS. It makes sense that they're given priority, since they're the things that are controlling the kinetics. But what about the orders. Remember those little exponents that tell you how important they are? The orders are the coefficients from the slow step of those substances. What coefficient is in front of each of those? They both have a 1 in the RDS. So ones. We don't show ones, but ones. Do you see the error you can make with iodide? See how he's a 2 in the overall reaction? That's the mistake to not make. The orders are the coefficients of just the slow step, which is 1 and 1. Now, I wish I could be like that's the rate law. Sometimes it is. Sometimes we're done right there. But sometimes I got to go all AP Chem on you. Look here. If the overall reaction has a reactant in it that isn't in the slow step, you have to add that reactant to the rate law with a 0 order to show that it is a reactant, but the 0 order shows that it's not controlling the kinetics. Listen to me say it again. If the overall reaction has a reactant that is not in the RDS, we're going to add it to the rate law, but we're going to give it a 0 order to show that it's not in the RDS. Do you see the issue here? Do you see the H plus? These two H plus are reactants in the overall, but not reactants in the slow step. So what I'm going to do is put the H plus there, but make it 0 order. And this is the finalized rate law. One last question I could ask though, what is the order of the overall reaction? It's 2, it's second order. Because remember how you find the order of the overall? You add. 1 plus 1 plus 0 is 2. Yeah! Let's see how far you can get on one of these. Thank you for that. Hey, look at this new problem. I'll erase that ink. If you look, I've got a list of the stuff I want you to find. But it's the exact same thing. Start by deriving the overall reaction, and then see if you can find all that other stuff. I'm just going to give you a 3-minute head start because I'm running out of time, but see how far you can get on answering these based on the new mechanism. I'm going to begin my analysis due to time, but you can keep working and just glance at me, whatever. Here I go. To find the overall reaction, I'm going to eliminate things that are reactants and products that are perfect matches. I see Hober and Hober, and then there's two Hobers. So that's perfect. I also see Huber and Huber. Get rid of them Hubers. But nothing else can eliminate. You're welcome to stop me if you disagree with something. Therefore, the overall reaction would be 4 HBRs, 4 HBRs, and an O2, giving 2 Br2s and 2 H2Os. 2 bromines, 2 waters. Somebody yell out an intermediate. Huber! That is the only intermediate, because intermediates are eliminated products not in the last step. It was made and consumed during the mechanism. All right, you see a catalyst? Yeah, we got Hober up in here. Hober. Because Hober was present during the reaction and regenerated at the end. Did you draw the acute energy profile?
Yes.
All right, so for the energy profile, how many humps did you do? Which one was the big one? There's an energy profile for you. All right, of course, it's energy versus time. And you could put an intermediate right there and a catalyst at the very end. The rate law. The rate law, well, it's always rate equals K. Right? Always starts with that. We'll start finding K values tomorrow. And then you go straight to the slow step. All right, here's the RDS right here. All right, and it's just the reactants of the slow step that go into the brackets here. My molarity brackets of HBr and O2. Now, what are the coefficients in the slow step here? They're 1 and 1 again, so it's ones, and we don't show ones. Do we need to add a zero order like we did last time? No, we don't, because remember, the overall reaction just can't have a substance missing in the rate law. So HBr and O2, HBr and O2, we're good. It's all covered. Everything in the overall was also in the slow step. What's the overall reaction order? Second. 1 plus 1 is 2. I know there's another slide in this presentation, but you don't have to go home and watch a video because tomorrow's lecture is shorter and I will cover it.